addition reactions. We're going to start with an alkene. We're going to be reacting it with some set of reagents, and we're going to end up with something like this, where we've added one of the two pieces of our original reagent to each of the two carbons of the alkene. So we're losing a pi bond, we're adding two sigma bonds, one to each of these two, in this case, atoms. Not particularly difficult. This is conceptually, it's the reverse of elimination that we talked about in the previous chapter. But these don't necessarily have to be, neither one of these necessarily has to be an H, and in many useful cases they're not going to be. For some very basic things, we need a couple of concepts that are going to apply to all videos for this chapter. One, regiochemistry. For us to demonstrate that, we're going to have an alkene that's not symmetrical to begin with. So the one that we're typically going to use is kind of a loaded dice example, this one. 2-methylpropene or isobutylene. The idea here is that we have a tertiary carbon and a primary one, so that we can kind of distinguish how the reaction actually functions. We're going to use that a lot. There's nothing magical about it. It just happens to have wildly different environments for the two carbons involved. That's one. Two, for stereochemistry. To see that, we're going to have to cut rotation out from what was this. We don't want that bond to free rotate. So if we want to have something where we can discuss the stereochemistry of how the reaction works, we're going to be looking at cyclic cases. There's any of them we could use, but basically most of the time it's going to be something like cyclopentene or cyclohexene, where once we're done, we're going to have either something like both of them on the same side, and or two of them on opposite sides, depending on how the reaction mechanism actually worked. So we're going to need to think about that with a lot of, just to be consistent. Again, there's nothing magical about this example. We could use any of a number of cyclic cases, but we use just so that we don't have free rotation. So as I said here, there's no free rotation. There is free rotation here. There would be after a reaction here. There is not here. Those two carbons cannot rotate away from each other because they're part of a ring structure. Remember that conformational stuff that you're still having nightmares about at night? Well, here it is again. No conformational motion, or very limited, versus unlimited. Simple as that. So with that lack of conformational motion, what it means is that this and this are not interconvertible. These are, in fact, as I'm sure you recognize, diastereomers of each other. Most of the reactions we talk about, we're talking only about relative stereochemistry. So that means that we're going to be looking at this plus it's an enantiomer. And we're going to be looking at this plus it's an enantiomer. In any case where one of these forms, we're going to get the enantiomer as well. We do not have enantiomer control here. We're talking about relative control of diastereomers based on how the mechanism works. We'll talk about that more in specific examples. The last piece of the puzzle here on the beginnings overview of this chapter is how does the reaction actually work? We have two basic concepts here. One, what's called asynchronous addition, meaning at the same time. This is a tricky thing that happens, but it looks like this. If I take something simple, like the example I had up earlier, so just an AB type thing, what asynchronous addition means is that basically I am simultaneously forming both of those new bonds and breaking this one, so that in what appears to be one step, both of those form. This is the rarest of the types, but it's also in some ways the most useful, because asynchronous addition, when I go and look at this in a cyclic case, for that to happen has to occur on the same face. So this has a stereochemical consequence. That we get only what we call a syn addition or a cis product when we're done. So synchronous meaning same time, it also means syn, if I could spell it, synchronous. It means syn or same face. And of course with the enantiomer. So that is the synchronous version. The other type of mechanism, of course, I'm sure you can guess, is asynchronous. The shorter version of that is stepwise. So in the asynchronous case, my first step is going to be looking at something like this happening, where we'll have one atom added and many cases of cation intermediate, and the second step will involve the other. So we'll talk about how this works specifically as we go along, but here I don't have a guaranteed stereo control because these things are coming in stepwise. I don't have an obvious stereochemical outcome the way that I have for a synchronous case. We're going to have to look at these in specific example cases. Depends on what we're doing, but we don't have a given stereochemistry by definition for a stepwise reaction unless there are some very specific tricks involved, and we'll get to those in specific examples as we go along. All right, one more thing that can help us as we're starting to work out how these reactions work and why is to violate the rules of resonance for a moment. Generally speaking, when we taught you resonance, we said a resonance structure that's valid should never have additional charged atoms. That is still true. However, in comprehending what's going to happen in some of these cases, it's helpful to draw what would be an invalid resonance structure just to conceptualize a few things. Here's what I mean by that. If I take the unsymmetrical alkene example again, I'm going to draw it 3 different times because we're going to look at it 3 different ways. I can look at this as breaking in one of 3 ways into resonance structures. The first, and thankfully for you, the rarest, is what's called a homolytic bond cleavage, meaning it breaks the same in both directions. When we want to draw single electron motion, we use these fishhook type arrows, and what that means is I'm splitting up pairs of electrons. So that resonance structure would give me this. I would have single electrons on both. Very rarely are we going to deal with that. There is at least one case in this chapter we're going to need that, but most of the time, be thankful, you don't need that one. It's not how things work. Second case. It breaks this way. Now, normal curve there. We're moving 2 electrons at a time here, just like we dealt with in the previous chapter. Now, we're looking at this. A negative charge here and a positive charge here. The other option, the last one on the far right, breaking the other way. In that case, now we're looking at a negative charge here and a positive charge there. Now, this should look familiar to you. We haven't talked about anions at all. So just pay attention to where the cation is in both cases. Here, it's on a primary carbon. If that sounds good to you, you probably don't want your score back from exam 2. Or here, it's on a tertiary carbon. That should sound very good to you. That's very good. So when we start looking at some of these reactions, we can already predict where it's likely certain things will happen by looking at this really bad resonance structure, but it helps us to conceptualize that if there's a cation forming during this, and at least intellectually we can say that as resonance, well, that's the where it's going to form. So if I bring in something to this, where I have something like this, where I have a reagent hypothetically like what I had before, but with charges, or with partial ones, well, where are they going to be attracted? They're going to be attracted to exactly where the opposite charge is here. So I can, basically using that, begin to predict where it is that the atoms I'm adding are going to end up. And it's going to make perfect sense to me. So we have some degree of predictability based on this sort of flawed resonance version of an alkene. Flawed in that it's not a good resonance structure. Doesn't mean that it's not valid. It means it's not a good explanation. But we can use it anyway. And by that saying it's not good is that just we don't like having additional charged atoms when we draw resonance structures. These would never exist this way separately, but we're just using it intellectually right now, which means we can do this. It is rational, this one is, whereas this one, much less so. This has a positive charge on a place where we generally would never find one. This has it in a place where it would be most stabilized by hyperconjugation.